Hey, this is Leach with Simpson Math, and in this video, I'm going to be talking about partial fraction decomposition. So it's the idea of taking one big fraction and breaking it up into its component parts of smaller fractions where our denominators are made up of basically prime factors. So let's get started. To get started, I'm going to look at the motivation for this. So if I see this fraction, notice this fraction has two different denominators, or sorry, this sum of fractions has two different denominators. We are subtracting it, and these two different denominators are prime factors. So there's fully factored. There's nothing else I can do to factor those. So let's add them together. To add them together, we need to get a common denominator. Well, the common denominator of these two, well, if we look at them, they have nothing in common. So basically, we need to give to one what the other one has. So I'm going to multiply this first term by x plus 6 over x plus 6, add to the other one, multiply to the other one x plus 2 over x plus 2. And we can do that because these orange parts are just 1. If you watch my videos, I call them fancy 1. Just multiplying by 1. I'm just putting a different mask on it. I can multiply by 1 whenever I want to. It doesn't change the problem. So I can take this expression, multiply my numerators out, go ahead and subtract. Be mindful because this example I chose had subtraction, so we need to distribute the negative. Big thing is between here and here, notice my denominator, I have common denominators, and when we add common denominators, when we have the same denominator, we just kind of smush those denominators together, but it's the numerators that get added or subtracted. And then further down the problem, we then just combine like terms, and we end up with this. So that means that we were able to start with these two separate fractions, and we're subtracting them, or adding them together. In this case, it was subtraction. And I ended up with this combined rational function, rational expression, where I have a polynomial divided by another polynomial. So I went from this side to that side, but how in the world can I go from this right-hand, from what was on the right-hand side, to what we started with? So how can I go from here to there? Well, the logic behind this is, so I know that if I'm looking at this denominator is x squared plus 8x plus 12. I could factor it to this x plus 2 times x plus 6. And then I can break that apart somehow. Somehow that breaks apart. But I would need to figure out what that numerator is. There's a lot of kind of weird, messy steps here that would be awkward to try to backtrack, because there's a lot of ways that could happen. So we're going to kind of logically jump to this step and kind of fill in the rest using algebra. So let's see how that would look like here. So I'm going to take my function, go ahead and factor that denominator. I'll have a summary of the directions in just a second that you can write down or screenshot. So we're going to factor the denominator if it needs to be factored. And then we're going to separate our denominators into partial fractions, and we will make them be a sum. And we'll collectively write them together as an equation. It's important that I'm just going to call it the partial fraction decomposition equation. And then I don't know what those numerators are. I mean, I do know in this problem, because I did make it in front of you, that it's going to be a 4 and a 1. But if I was working this problem from scratch, I wouldn't know that it's 4 and 1. So I'm just going to fill them in with some placeholders of a and b. You might be thinking to yourself, well, how's that possible? Aren't there a whole bunch of other possible things? One caveat to doing this process called partial fraction decomposition is that this fraction, this rational expression, needs to be bottom heavy. What I mean by that is that the degree of the denominator needs to be larger than the degree of the numerator. If it's not, you can use some process like long division to accomplish that goal, to get rid of the extra parts, so that way it is then bottom heavy. We'll see that at the end of the video. So because the fact that this is bottom heavy is what will enable this to happen, one important note is that the numerator is going to be 1 degree smaller than the denominator, specifically the base factor of the denominator. In this case, it's just going to be some constant. We don't know what they are, so I'm just going to, as a placeholder, leave them to be a and b. As a convention, we've chosen capital letters, just so that way they're distinctive from our variables. I'll talk a little bit more about the distinction in a bit. All right, so again, so we factored. We've separated this because we know that somehow this thing should equal that. I just need to figure out what those a and b are. So again, like I said, this is an equation. They do equal each other, so I'm going to use that fact that they equal each other to help me kind of solve this. There is an issue that we'll have to work out with, is that this equation is it's one equation, but there's three unknowns. I don't know A, I don't know B, and I don't know what my x's are. So we'll get there. So in order to deal with this, first let's get rid of all these messy denominators. So I'm going to take my factored least common denominator and multiply everything by the least common denominator. I really, really encourage you to show this step so that it's very physical, where every term gets multiplied by the least common denominator, left side and right side, and that's why the x plus 2's go away, the x plus 6's go away, because they reduce to 1 because I'm multiplying by this. And I can do this multiplication because I'm multiplying both sides of the equation. Earlier when we were doing this, this was just an expression, so my only option was to combine terms, or in this case I multiplied by fancy 1. Here I am not multiplying by 1, I'm multiplying by x plus 6 times x plus 2 over 1, but I'm doing it to the entire equation, basically both sides of the equation, and then distributing. And I can do that because it's an equation. So multiply everything by the LCD. The denominators are going to reduce. Notice I'm going to be left with this x plus 6 on the a term, and I'll be left with the x plus 2 on this b term. And so we'll write that out. So now I have just this numerator equals a times x plus 6, and then b times the x plus 2. Put a little star here, because in a second I'm going to come back and show you an alternate method for determining a and b. So we have our equation here. We can now FOIL. Well, actually not FOIL here. Sometimes it might FOIL, but here I'm just going to distribute. And then I'm going to combine like terms. So my like terms, I see this bx and this ax. So those x terms, let's put those in the front. And our constant terms, let's put those together at the end. So here are my x terms. Here's my constant term. And I really encourage you to then take this extra step. And I'm basically going to be factoring out my x. I'm not factoring out a GCF, but it will feel like that. If there was a GCF, like if both of these had a 2, I would leave those 2's inside. I'm not factoring out a GCF. I'm just specifically factoring out the x. So I go, okay, well, those both have an x in common, and I'm going to factor them out. And I'm intentionally putting it at the end. I'm putting it after the a plus b, so that way it feels like a coefficient, because that's what it is. So I now have this equation where I have 3x plus 22 equals all of this. Notice I have a linear term, constant term, and the left side equals the right side. So you could argue that 3x equals a plus bx. I could further argue that 3 equals a plus b. And it does. So this is a little bit of math magic, but I can pull these two things out and set them equal to each other, because I'm just kind of using logic here. I'm saying, well, logically, 3, the coefficient of the linear term, has to equal a plus b, the coefficient of the linear term on the right. So 3 equals a plus b, and then my constant term on the left should equal my collective constant term on the right, 6a plus 2b. Notice what's happened here. We've gone from an equation with 3 unknowns. I don't know a, I don't know b, I don't know x. We've gone from an equation with 3 unknowns to a system of linear equations with 2 unknowns. If I have a 2-equation system with 2 unknowns, 2 equations, 2 unknowns, when the number of unknowns and equations match, it's solvable. So I'm just going to use my knowledge of systems of equations, so substitution, elimination, those sort of things, and let's solve for our unknowns. So I could do substitution, but here I'm going to do elimination. I'm going to multiply this top equation, so I'm doing negative 2 times row 1, multiplying negative 2 times row 1, sticking it here. And then I chose that to kind of attack the b's. I want the b's to go away. Could attack the a's, but the b's would make smaller numbers. So multiply by both the entire top equation by negative 2. So all 3 of these change their sign and get 2 times bigger. A negative 2b plus 2b is 0. When I add these together, add negative 6 and 22, I get 16. Add negative 2a and 6a, I get 4a. And then I could just solve 16 equals 4a, divide by the 4, and I get 4a. All right, so now that I know what a is, I can quickly find out what b is by just plugging it into this top equation. So I plug in the 4, subtract the 4, and I get negative 1 is b. So a is 4, negative 1 is b. I probably take too many steps to get here, but just for note purposes, I want you to see that I have this statement, I have this equation. I'm going to replace the a and the b with what I know that they are, and then simplify if I need to. And so instead of adding a negative, I'm going to turn that into a subtract 1. I did FOIL this back because the original version had it foiled. If you FOIL it back, cool. If not, whatever. It doesn't really matter. The important part is them going from, I went from this fraction to these sum of fractions with these separate components. So if we go back and look at what we did when we started, oops, too far. We started with this and went here. What we just did using partial fraction decomposition was going backwards. Why might you need to know this? Well, if you, this is, my audience here is for my college algebra class. If you're going to be taking calculus, especially like Cal 2, when you do integration, sometimes trying to do the integral of this thing is gross. But if we break it up into smaller fractions, then I could do partial fraction decomposition, then I can integrate both of these, and that's much more manageable. So that's the idea behind this. Sometimes it's messy to do with this, so we just break them apart into their smaller fractions. All right, so here are the general directions. If you want to take a screenshot of that, feel free. I'll pause for a second so you can see the whole thing. All right, let's look at them a little bit closer just so I can make it a bit bigger for you. All right, so the idea here, so one, we have this note that when we do PFD, it needs to be bottom heavy. Bottom heavy meaning the degree of the denominator is larger than the degree of the numerator. If it's not, then we'll do long division to fix that. Then, step 1 basically is to set up the partial fraction decomposition. That's what I'm abbreviating PFD for. We're going to set up the PFD equation where the original fraction is set equal to the sum of the partial fractions. The original fraction can be the factored version. That's cool. One note is, notice I'm going to be factoring the denominator if we need to. If the numerator factors, cool, but it's not really necessary and it's probably going to kind of get in the way. So leave the numerator unfactored. The only reason why I would want to check to see if the numerator factors is just to see if anything reduces, because if it reduces, then it will make the problem be a little bit easier. Often these numerators aren't even factorable just because the way that these PFD problems work, though at least the nice ones they kind of be a jumbled mess in that numerator. So you could check it, but it's not really necessary for the process. So if necessary, we do need to factor the denominator into the smallest prime factors. So make sure to go all the way down until you get to a prime factor. So I don't need to force x squared minus 2 into be x plus square root of 2 and x minus square root of 2. We don't want that because that's gross. So leave the factor in something like that into x squared minus 2. Don't try to force it into something else. This would be a prime factor. If you end up with like x times x, we will write that as x squared, but it's helpful to know that those are actually the prime factors would be an x and then another x. That's what I'm talking about when I mean we have a repeated factor, if I have multiple of the same factor. All right, so factor down to the smallest prime factor. Then the denominator of our partial fractions will be each factor in the denominator, and this is an important note. We're going to use increasing exponents for each repeated factor. We'll see that example coming up. Then the numerators of the partial fractions will be the polynomials 1 degree smaller than the degree of their denominators. So for the problem we just saw, they were linears. These are linears in the denominator, so I have constants in the numerator. Later we'll see one where I have a prime quadratic factor, so something like x squared plus 2 or even x squared minus 2. Both of those don't factor nicely, so we would just leave them in that form. And then, but the numerator would be a linear. It'll be a linear like something like ax plus b. So just to note that it says for repeated factor. Oh, and we're going to use those capital letters like we saw. For repeated factors, we're going to use the degree of the base factor, that base prime factor. So what I mean by that is, if we see x plus 3 squared, that is x plus 3, the linear factor x plus 3 that's been repeated. So that would have a constant numerator. But something like x squared plus 3, that would have a linear numerator because this is a prime quadratic. All right, Then here's the steps for what we went through, just a general solving. So we do need to multiply both sides of the equation by the LCD. This reduces all denominators, so that is a necessary step. Then steps 3 and 5 are kind of optional, kind of not. We'll talk about how they could be skipped if you want to on some problems, but not all. That's the general process of manipulating, getting the system of equation ready. And then lastly, once we find A, B, and C, then we substitute it back in. So if we look back at this starred step we saw earlier, here, I could just use some logic to determine A, B, and C. Again, this will work sometimes, but not always. And sometimes it might help us find the A or the B, but maybe not the B, maybe not the C or something. So it'll help us find maybe one or two, but not all, is often the case. Or sometimes just the work is going to be grosser, and so you just don't want to mess with it. All right, so one note is that I'm thinking of x as a variable. It is an unknown, but it's a variable. I could graph this this function, and then x could basically take on all real numbers except for where it doesn't exist. So it is a variable. This a and b, they are a specific value, a singular specific constant. I just don't know what it is. All right, so x is taking on a whole bunch of variables, all numbers, a whole bunch of values, basically kind of all values at once. It's representing a whole bunch of values. It's a variable, whereas a and b is just an unknown constant. It's just a question mark that I'm trying to determine. All right, so what we're going to do is we're going to choose a convenient value for x to help us find a and b. So notice here, if I choose -2, so if I was to plug in a -2 into all of these, look what happens to the b term. What's -2 plus 2? Well, that's 0. 0 times b is just 0. So notice if I plug in a -2, the b term goes away. And I'm just left with a one equation, one variable of 16 equals 4a. I can divide by the 4 and I get a is 4, and that's what we saw earlier without having to make that system. Likewise, I could plug in a -6 into every x. When I plug into a -6 into every x, notice the a term goes away, and I'm just left with -4b. -4 times b. Pay attention, the left side is still receiving treatment. I'm plugging in that -6. So I get 3 times -6 is -18. -18 plus 22 is that 4. So this left side is different on both of those because I'm plugging in a value into the x's. So that's why the x's go away when I'm plugging a value for it. And then sometimes if I can make all but one of the values go away, then I'm able to produce a nice equation that way. All right. So just for practice, if you want to decompose this algebraic fraction, this is very similar to what we just did. You will need to factor that denominator first. So take a second, pause the video, and try this one on your own. Go through those steps and decompose this fraction. All right, so you should have what I have. So we factor this fraction, this quadratic. We have x squared plus x minus 2. So if I do the AC method, I get AC of -2. What multiplies to be that -2 and adds to be a +1. Well, that's going to be a -1 and a +2. And since a is 1, we can jump. So we end up with x minus 1, x plus 2. So each fraction in my partial fractions will get one of those unique factors in the denominator. These are linear factors, so I'm going to have constant terms up top. So I'm going to have that a times b. All right, now I'm going to multiply by the least common denominator. So every term gets a x minus 1 times x plus 2. You get x minus 1 times x plus 2. You get x minus 1 times x plus 2. You get x minus 1 times x plus 2. Everybody gets an x minus 1 times x plus 2. Be the Oprah of giving out x minus 1 times x plus 2. So every term gets it. You should have no more denominator. Every denominator should reduce out. I like this step. Please, 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 please do this step for your sanity so that you can physically see the denominators going away. On this left-hand side, do write what it equals. It equals 4x minus 1. It does not equal this anymore. It equals just this numerator. I am in my notes writing 4x minus 1 every time, the left-hand side. If you want to get away with maybe not writing it, you can maybe not write it in these in-between steps, but this first time we see it and the last time we see it, it should be there. All right. That when we do that, oh, and the equal sign should always be there. So always the equal sign. So it's just not writing those few digits. So just write it. All right. So then I have a times x plus 2, b times x minus 1. So we have here. If you were to do the shortcut, it would work pretty well. Plug in a -2 for your x, and you get b as 3. Plug in a 1 for your x, and you get a as 1. And then I'm done. I would jump down to my answer and be like, I'm done. I did it. If you didn't do that, then we would need to do the distribution steps. Combine like terms, put your linear terms together, constant terms at the end. Then factor out the a as a nice visual step, that a plus b is my coefficient. So 4 times a plus b, and then -1 times 2a minus b. And then we end up with, one sec, I got a text I need to, all right, so then we end up with this system of equations, 4 equals a plus b, and -1 equals 2a minus b. All right, so now that we have that, I can then just solve the system. I notice that I have a positive b and a negative b. So if I add those, the b's go away. So I have 3 equals 3a. So then a is 1. And then plug that into one of the other equations. Top one seems nice. And I get that b is 3. So notice I get the same things that I saw earlier. So that if I was to break this fraction apart into its partial fractions again, where the denominators are more or less the prime factors of the denominator. I have 1 over x minus 1 and 3 over x plus 2. All right, so I'm just going to go a little bit faster through the rest of them. I think I've kind of shown that process. I'm going to show how can it get more difficult. Well, this first one can get more difficult because notice I have my degrees are bigger. This is still bottom heavy, so I can still do this, but my degrees are a little bit bigger, and that factoring process is a little bit messier. So I do need to use the partial fraction decomposition method to factor this cubic. The reason why is I try grouping, but we see that that's going to fall apart pretty quickly. I can't factor by grouping. It's a cubic. There's no GCF. I can't do the AC method, so we got to use possible rational root theorem. So that's what I have here. So just quickly, I write out my possible rational roots. I test 1, I see it doesn't work. Test -1, it does work. And I'm testing that by just plugging in the values using the remainder theorem, because if I plug in the value, whatever that equals will be the remainder, and I'm seeking a remainder of 0. 1 and -1 are pretty quick just to plug in. So when I do that, I see that -1 works, which would be the factor x plus 1. The root is x minus 1, the factor is x plus 1. So -1 works, which leaves me with x squared minus 6x plus 9. Remember, once you get a quadratic, you should have the skills at this point to be able to factor any quadratic in the world, either by factoring, solving by square root, or by the quadratic formula. So here I have successfully factored out the x plus 1, which leaves me with x squared minus 6x plus 9. But because I can keep factoring, this is a quadratic. I now have x minus 3 times x minus 3, or x minus 3 squared. So if you look back at the directions, when we have repeated factors, we need to work with, our denominators need to have ever increasing exponents up to the exponent on the factor. So here we're going to go from this left-hand side to this right-hand side. So I've factored my denominator. There's my factoring on my denominator. All right. Then we'll obviously have this x plus 1. We're good with that. And I think most students are usually probably obviously good with the x minus 3 squared, because if this wasn't here, well, then my least common denominator would be x plus 1 times x minus 3 squared. But this could be there. Let me backtrack to an example like this. If I have 3, 2, and 4, if those were my denominators of a fraction, so don't worry about what's up top. If those are my denominators of some fraction and I'm adding them up, the least common denominator would be 12, not 24. Because there's this 2 that's inside of that 4. So we just go, oh, well, that's 3 times 4 is 12. The least common denominator is 12. Because there's that kind of, there's a shared factor between this 2 and this 4. But this 2 right here, that 2 could still, that 2 is still part of that, even though even though it doesn't have an impact on the least common denominator, it is still there. So this x minus 3 is a possibility. It could be there. Now, when you're working this problem, b might be 0. B could be 0. If b is 0, that's fine. That'll be determined when we do our work. But if we don't include it, then we're not allowing that possibility of that b being a 0, and that's a problem. So if b is a 0, it'll be revealed that it's a 0 later. So that does need to be included. I have some examples later of just kind of some what-ifing with that a little bit, but that's a big part. We have repeated factors, include each one up until you hit the, so start at 1 and you work your way up until you hit the exponent that you had. All right, then the math is the same. This particular one is a little bit messier because we now are encountering some quadratics. So when everything reduces, I have this x minus 3 squared, or I have this x plus 1 times x minus 3. So we have some quadratics, which is fine and expected because look at our left-hand side. It's a quadratic. So because of that, I have this quadratic equals a quadratic after I get that all done. So notice here, I do factor out the x squared. I factor out the x. And then I'm able to say, well, 7 logically has to equal a plus b. So I do that. Negative 35 has to equal all of this. And 22 has to equal all of this. And so that's where I get this equation from. Now, if you try to do the shortcut, it does work nicely for 3 and negative 1. You get c is negative 5 and a is 4. But it doesn't work so nicely for the b. So the idea here is you could save a little bit of time with doing this, get to this point, and then go ahead and just plug in what we know about a being 4, and then we can get that b is 3. So without having to do the full system, I could kind of use a little bit of that shortcut and then take our system and plug in that way. All right. If you didn't do this, then we would need to do the full system. So I chose to take these two, pair them up, and get rid of the c's because I look at my top equation, it's missing the c term. Because it's missing the c term, let's get another equation where the c term is missing. So then we're going to do that, get rid of the c term. I multiply this second equation by a negative 1, so that just changes all the signs. So that way when I add them up, the c's go away. And I'm left with this 57 equals 15a minus b. Grab that top equation. I notice that my b and negative b's will then add together and cancel to 0. I don't have to do any extra work there. So then I get a is 4. Take that a is 4, and let's plug it into my top equation, and I get that b is 3. Take both of those, plug them into either of these. I chose the bottom one, and I get that c is negative 5. If it's a negative, do make sure that we change the plus to a subtraction. All right, what about this one? So if we were to decompose this function, notice I'm just calling it a function here. It's the same idea. I have this function. I'm wanting to decompose it. Factor our denominator. This is factorable by grouping, so yay that. But this x squared plus 4, that is a prime factor. That is a prime quadratic factor. That can't factor any further. If we were to force the factoring, it would factor into x plus 2i and x minus 2i, I believe. Those are imaginary factors. They are not real. And so that's why this is a prime factor. So we're not doing that. So leave it in its prime factor state. But the problem is, this is a quadratic. And so I want this numerator, because, pause for a second. Remember the caveat that in order to do PFD, this needs to be a bottom-heavy function, or bottom-heavy fraction. So that's why we allow for the possibilities where the numerator is 1 degree smaller than the denominator. Now, it could be possible that there is no x and this could just be a 0. But we need to account for that possibility. So 1 degree smaller is what we're going for when it's a prime quadratic. If it's a prime cubic, 1 degree smaller, and it would be a quadratic in the numerator. So I'm going to have a basic linear equation here with the placeholders in my linear term and the constant term. So I have a bx plus c in that numerator. Then everything else is the same. Multiply by the LCD, all the denominators reduce. Distribute, combine like terms, get your squares together, your linears together, your constants together, factor out as necessary to find your coefficients. So we see that 3 equals a plus b, negative 2 equals negative 5b plus c, and negative 7 equals this 4a minus 5c. I could easily determine that a is 2 by plugging in x to be 5, but there's not really an easier path otherwise. All right, so then I use my system. I could use my system and my knowledge that a is 2 to quickly find the others, or just solve using systems of equations. I went the substitution route because I have each equation just has 2 different terms and they don't really overlap. So I just did substitution. So just took, I solved the top equation for A, plugged it into the purple equation, solved the second equation for C, plugged it into the purple equation. Now I have one big purple equation, one big equation with just my B unknowns. That's cool. So I do that, plug it in, simplify, and I end up solving for B equaling 1. Once you know that B equals 1, and I have an equation with the B and one other value, I'm going to take that B and plug it in, and I get 2. I'm going to take that B and plug it into the second equation and get that C is 3. So A is 2, B is 1, C is 3. Plug them in, and there you have it. All right, so I want you to look at this one. I'm intentionally not showing you the result. If I have this fraction, 2x plus 1 over x minus 5 squared times x cubed, how would you just set up that partial fraction decomposition? How many fractions do you have? Is it 2? Is it 3? Is it 4? Is it 5? Is it 6? It's one of those. And then what's in the denominator of each? And then lastly, what do those numerators look like? So if you haven't done it yet, take a second and figure out what that would be. All right, before I reveal, I'll tell you there are 5 fractions from this. All right, so let me show you what I have. So I have x minus 5 squared. So that linear factor is occurring twice. So I need to include the base version just to the first power, then to the second power. Then I have x cubed. I have x occurring twice. It's x times x times x. So that x is occurring, that linear factor is occurring 3 times. So I'm going to include an x squared, and then an x cubed. So you must include every value leading up to it. And then these are base, every one of these factors are base linear factors. So this is x minus 5 times x minus 5 times x times x times x. If I was to write it out without the exponents. So notice those are all 5 linear factors. Since they're all linear factors, my numerators are just going to be constants, 1 degree smaller. So I have this note, just to clarify, when the denominator of a partial fraction contains the power of a linear factor, we're going to have constant numerators. When the denominator is the power of a prime quadratic factor, then we have linear numerators. So I'm talking about a power of a power of a linear. This is a linear that's been raised to some power. So that's why they're constants. All right, this last one, something you might encounter, but it's a little bit more big picture. Notice with this one here is the last example. It's top heavy. We cannot use the partial fraction decomposition method with this because it's top heavy, because it's going to mess up this whole numerator situation where I'm saying that the numerator needs to be 1 degree smaller of the base factor. Because if it's top heavy, then it's like, when would you stop if it's top heavy? Like, if I have a x on bottom, would I include an ax plus b? What about, do I have like an extra squared? Like, when would you stop? That path, that process is complicated. So that's why it has to be bottom heavy, because it kind of limits the complexity. So what we're going to do is we're going to do long division. So I'm going to long divide, just like if you're trying to determine your in behavior asymptote, you could just do long division. So take our denominator, there's our numerator, do our long division. My quotient, I'm not going to go through the steps of it, that's for another video. It's actually the last one I recorded. So my quotient ends up being 2x plus 15, that's the quotient. If we are graphing this, if we're making the, if we're like trying to graph this, this would be my in behavior asymptote. Some people call that a slant asymptote. This would be the in behavior asymptote. Then we have this remainder. Look at my remainder, this divided by that. Look at that remainder. It's bottom heavy, isn't it? So this is what we're going to use to determine our partial fractions. So actually, arguably, these kind of are part of our partial fractions. They're just over 1, which are prime factors in a way. So we already have these things broken out. I need to break that out a little bit more. So we're able just to do our partial fraction decomposition. It's going to say, hey, I'm doing PFD. So kind of like, hey, let me just do the PFD work. So I'm only focusing on this. I'm going to come back and put that in at the end. So I'm just going to focus on that work here. So factored x squared minus 7x plus 10 into x minus 2, x minus 5. So there's nothing in common. There's no repeated things. So it's just x minus 2, x minus 5, a and b up top, multiply by the LCD. You could shortcut it and see that b is 30 and a is 14. Or you can go ahead and distribute combined like terms. You get a system of equations like this. Again, you get a is 14 and b is 30. So focusing in over here, just to simplify the remainder part, a is 14, b is 30. All right. Recall also that, let me put a little line right here. There. So recall also that the function is all of this. I just focused in on here and saw what it equals. So I'm going to replace this with what it equals. So now I know that the function, I should have a celebratory box here. Our function is, if I break it out into its kind of partial fraction parts, I have two that aren't visibly fractions. There are an over 1 there if I wanted it, but I have a 2x, I have a 15, then I have a 14 over x minus 2, and a 30 over x minus 5. All right, so that is partial fraction decomposition. It's about as hard as it gets. In college algebra, it might be typical for you to, the only way that I've seen it really get harder is if your denominator is made up of 2 quadratic factors. It's just the same part. The math in it, the math here just gets a little bit messier, and you do have both of those would be linear. That's about as hard as I've seen at least for at the college algebra level. The main thing is this is a tool that we want you to have in your toolbox, so that when you take like calculus at Cal 1, maybe Cal 2, for sure Cal 2, that when that instructor goes, oh, now we need to do partial fraction decomposition, you go, oh, I remember doing that. Might need a refresher, but I remember doing that. That's the goal behind this. All right, so I hope this video helped you understand partial fraction decomposition a little bit better. Take care, and I'll see you in the next one. Bye.